Thank you for the introduction. So I'm going to talk about a common problem in ReaderWriter Locks, which is the scalability of those locks in the presence of multiple readers. So a ReaderWriter lock is a synchronization primitive for controlling access by multiple threads to a shared resource. These locks allow shared access for read-only use of a resource, while write operations access the resource exclusively. Those locks are common in modern systems, ranging from databases and key value stores to file systems and operating system kernels. ReaderWriter locks have to keep track of the presence of active readers before a lock can be granted to a writer. In the common case, a shared counter is used, which is incremented and decremented with every acquisition or release of the of the lock in the read mode. Now, when a writer shows up, it reads the value of the counter and it waits until it drops to 0. This approach results in a very simple and compact lock, and in fact is found in common ReaderWriter lock implementations, such as those used in the Linux kernel, POSIX pset library, and many other places. However, this approach suffers under high-intensity read-dominated workloads when the reader indicator state is updated frequently by a diverse set of threads acquiring the lock for read, causing cache invalidation and coherence traffic. Alternative designs for ReaderWriter locks employ distributed reader indicators, one per NUMA node, one per core, or for example, one per thread. Now, this improves reader-reader scalability, but also considerably increases the size of each lock instance. Furthermore, the lock performance is hampered when writes are frequent, because now multiple indicators have to be checked and or modified when a writer shows up. Plus, as a minor issue, such locks cannot be instantiated statically, since the number of NUMA nodes or cores or threads is typically not known until the runtime. And that might be an issue for certain applications. So as a result, designers of modern ReaderWriter locks have to face a difficult trade-off related to the scalability and footprint of maintaining the indication of reader's presence, forcing them to choose one feature over the other. In this work, we introduced Bravo, which essentially eliminates the reader indicator dilemma and allows a ReaderWriter lock to remain compact and scalable in the presence of multiple concurrent readers. So Bravo augments any existing ReaderWriter lock, adding just 2 integer fields to the lock instance. In addition, it adds a visible readers table of fixed size that can be shared by all threads and locks in the same address space. Now, those 2 new fields are called rbias and inhibit until, and their meaning will become clearer over the next few slides. For now, I'll only mention that rbias is just a flag that can be easily collocated with this new inhibit until field. But for clarity reasons, we didn't do that in our work. So with Bravo, readers make their presence known to writers by hashing their thread's identity with the lock address, forming an index into a visible reader's table. Specifically, they read the value of the rbias flag. And for now, let's assume that the flag is set. Later, I will explain how we determine the value of this flag. So if the flag is set, the reader will attempt to install the lock address into the slot in the table identified by the result of the hash function. This attempt is scaled by an atomic concurrent swap operation. And if successful, the reader can proceed with its critical section without modifying any shared state of the underlying lock. Now, when another reader shows up, it will essentially follow the same procedure, but now using its thread identity, will typically choose a different slot in the reader's table, and so make its presence known in that slot. One may wonder what happens in the case of a conflict. So for instance, if a third reader shows up and picks a slot that is already occupied by another thread or another lock. So in this case, the concurrent swap operation will fail, and that reader will simply resort to the acquisition path of the underlying lock, which in this case will simply increment the shared counter. Note, however, that collisions are benign and impact performance, but not correctness. And the odds of collisions are equivalent to those given by the birthday paradox and dictated, among other things, by the size of the table and the number of threads. So as I already said before, the table is shared by all threads and locks in the address space. Crucially, though, threads acquiring the same lock in the read mode tend to write to different locations in the table, reducing coherence traffic and resulting in a NUMA-friendly design. In a nutshell, this is the key for Bravo to be able to accelerate read-dominated workloads. Now let's talk about writers. So when a writer shows up, it always uses the acquisition path of the underlying lock. So first it acquires the lock for write, and then it resets the RBias flag. And by doing that, it prevents any new reader from using the table for the fast read acquisition. Now, after resetting the RBias flag, it scans the table, waiting for any existing reader that acquired that particular lock through the fast path. Obviously, doing that revocation scan for each and every write acquisition would be prohibitively expensive. Therefore, a simple mechanism is put in place to limit the overhead of scanning the table for workloads in which writes are frequent. Specifically, the writer measures the latency of the revocation scan and then inhibits the subsequent setting of the bias for the duration of that time multiplied by some constant factor. So the factor is chosen that the worst case expected slowdown from Bravo would be below certain threshold. So in our case, we chose the factor of 10%. So to give you a concrete example, for instance, if the revocation scan takes 10 milliseconds, we inhibit setting the RBias flag for the next 100 milliseconds by writing a timer value into the inhibit until field, and thus effectively disabling Bravo for the next 100 milliseconds in this case, and using the acquisition functions of the underlying lock instead. Now, this scheme is oversimplistic and might be too conservative, but we found that it's actually working really well in practice and very simple to implement. With that, I can finally explain how we set the RBias flag, and that's pretty straightforward. So when a reader acquires the lock in the read mode, it checks whether the RBias flag is not set and whether the current time is larger than the value currently written in the inhibit until field. If that's the case, it sets the RBias flag, essentially enabling subsequent read acquisitions to follow the fast path and use the table again. So this essentially concludes the technical presentation of how Bravo works, and now I would like to talk about our evaluation. So the goals of our evaluation were to show that Bravo is easy to integrate with existing locks, it's compact, it accelerates reads, and it handles writes gracefully, so it doesn't slow down writes. And we achieved those goals both in the user space as well in the kernel. So for the first part, to demonstrate how Bravo can be integrated easily with existing locks, we did the integration with the compact and efficient Brandenburg-Anderson, or BA ReaderWriter Lock, as well as with the POSIX pthread ReaderWriter Lock. So from the perspective of Bravo, POSIX pthread lock is really an opaque lock implementation. We built Bravo as a wrapper that can be used with any ReaderWriter lock in the user space. Furthermore, we integrated Bravo with the Linux kernel RW semaphore, and I'll talk about this integration later, but I'll just mention for now that in each and every case, including the kernel, the integration of Bravo requires just a few dozen lines of code. Now, this slide shows the memory requirements for Bravo, taking the BA lock as an example. The BA lock requires just 40 bytes for its 4 pointers and 2 integer fields. Bravo adds 2 fields, which conservatively require at most 12 bytes, even though, as I mentioned before, those two new fields can be collocated and use even less memory. Note that if the lock is padded and aligned to the size of the cache line or cache sector, which are typically 64 or 128 bytes, and that's actually padding and aligning locks is a common practice in real deployments. So both Bravo and Bravo integrated, both BA and the BA lock integrated with Bravo require just 1 cache line or 1 cache sector. Of course, in Bravo, we also have the cost of the visible readers table. Now, for our experiments, we selected a table size of 4,000 entries, or 4,000 pointers, And that selection was made empirically. But in general, we believe that the size should be a function of the number of logical CPUs in the system, much like the Fulex tables are sized in the Linux kernel. With that, the memory size of the table comes down to 32 kilobytes. But this cost becomes amortized and negligible when thousands of reader-writer locks are used in an application. Now, in comparison, we also include two locks with distributed reader indicators. One is called per CPU, as its name suggests. It uses a per CPU reader indicator, which in our system with 72 CPUs comes down to over 9,000 bytes. Now, another example is cohort RW lock, which uses a reader indicator per NUMA node. And on our dual socket system, these logs come, the footprint of this log comes down to almost 900 bytes. Note that this is the cost for each and every such log. It's not amortized when more logs are used. Now, on this chart, we compare the performance of BA and pthread reader-writer locks with the variants that use Bravo. As a baseline, we also include the two logs with distributed reader indicators from the previous slide, the cohort RW log and the per CPU. The workload here is generated by a synthetic benchmark where threads perform local operations inside and outside of the critical section protected by reader-writer lock, where in this case, the lock is acquired for write only in 1 out of every 10,000 operations on average. So the workload is really read-dominated. So here we show the throughput, and the high is better. And we can see at the bottom of this chart that both BA and pthread reader-writer locks do not scale at all as we increase the number of threads. And that's because they use the contended reader indicators, which yields flat performance. Now, cohort RW yields modest improvement to the performance, but the interesting point here is that Bravo BA and Bravo pthread scale really well and perform similarly to the per CPU lock while using just a fraction of its memory. Now let's see what happens when the workload includes more write operations. So in this case, 9 out of 10 operations are writes on average. This workload is very write-heavy, and we see poor scalability over all the logs just by the virtue of the highly serialized nature of the workload. The per CPU log at the bottom of the chart fares particularly poorly as write operations, which are common, need to scan the entire array of per CPU reader indicators. Now, the interesting point here is that the Bravo BA and Bravo pthread logs track closely to their counterparts without Bravo, providing neither benefit nor harm, as we would like to see. So there are many interesting points between 90% writes, as in this chart, and 0.01% writes, as in the previous chart. And our paper includes charts for many of those points. In the paper, we also present results for other benchmarks, including the popular key value store RocksDB, for which Bravo also provides a dramatic improvement to the scalability of the underlying reader-writer locks. However, I would like to show that Bravo can be beneficial not just to user-level logs, but also to synchronization constructs found in the operating system kernel. As an example, we demonstrated by integrated Bravo into the RW semaphore in the Linux kernel. So the RW semaphore is implemented with a counter and a waiting queue protected by a spin lock. The counter keeps track of the number of readers and also records the presence of the writer. Now, when a writer is not present, the acquisition of the RW semaphore for read boils down to just one atomic counter increment. Note, however, that this read acquisition creates contention over the cache line hosting the counter, which is where Bravo can be useful. Now, the reason that we chose to focus on RW semaphore is because one of its instances, called mmap-sem, is a serious, well-known synchronization bottleneck in the kernel. mmap semaphore protects access to the virtual memory area, or VMA, of a process. So every VMA operation, such as mmap, munmap, or pagefold interrupts, acquire the mmap semaphore, creating contention for data-intensive applications. Now, to evaluate the impact of Bravo on the performance of mmap semaphore, we used WillScale, which is an open source collection of benchmarks for stress testing various kernel subsystems. In our case, the relevant benchmarks were page fault and mmap, where page fault creates mostly read-dominated workloads, since page fault interrupts require mmap semaphore for read, and mmap create write-heavy workloads, since those separations acquire the mmap semaphore for write. So on those charts, we can see that in the page fault example, again, we show throughput, so higher is better. The Bravo version scales across all thread counts, while the stock version stops scaling after about 16 threads, when the contention on the counter and the RW semaphore becomes significant. At the same time, mmap exhibits no significant difference in the performance of Bravo versus stock, confirming empirically that much like in the user space, Bravo doesn't introduce overhead in scenarios where it's not profitable. So in summary, Bravo is a wrapper that can be easily integrated with any reader-writer lock. Bravo accelerates reads by reducing coherence costs that would normally be incurred by locks having a central reader indicator. Write performance is left unchanged relative to the underlying lock. Bravo incurs very small footprint increase per lock instance, and overall, it takes the reader indicator dilemma away. So with that, I would like to thank you for your attention, and I'll be happy to take your questions.
Abhinav Duggal, Dell. So if in the current reader-writer lock, the reader-writers are only affecting each other, but they're not affecting each other, they're only affecting their own lock. But in this case, because you have a common table, any writer is affecting everyone else. So isn't that a problem? Won't any writer cause all the readers and the writers to actually get stalled?
So the conflicts indeed can have impact on the performance. Right, in our paper, we include evaluation of an experiment where we measure the impact of those conflicts. Right, and we show that compared to an optimal case where there are no conflicts at all, where each thread will use a separate table, thread local table, the impact of those conflicts is very small, something like less than 6%.
And how do you handle a situation where the table is not big enough? Because you need to know how many locks that can fit in a table. So if the lock exceeds, what do you do? Right.
So in our work, we have actually in the paper we stated list of directions, future directions that we would like to explore, and the first one on this list is dynamic table sizing. Right. So we can try to increase the size of the table just by measuring the rate of collisions and do that dynamically, and that's we can size the table according to that.
Okay, thank you.
Sure.
I was wondering if you compared this to MCS locks.
So MCS locks are not reader-writer locks, right?
There are MCS reader-writer locks.
Oh yeah, there is a variant of MCS reader-writer lock. And no, we haven't compared to those.
Sudarshan Rutgers. Have you encountered cases either in the Linux kernel or applications where the revocation time was high or where you had to exponentially back off because of the revocation?
Sorry, can you repeat the question? Have we encountered
applications where the revocation time was high? Because let's say if there is a writer that's waiting for all the readers to complete, and you have to keep waiting for the readers for the writer to.
Right. So the revocation can be expensive, right? But that's why we have this mechanism in place so that we ensure that it will happen once in a relatively long while. Now, the other point that I want to highlight that probably once in our lifetime we finally have the hardware prefetcher working in our advantage, right? So when we scan and there are not that many readers around, the prefetcher will make the scan much more efficient. Now, another point is that while we wait for one reader that we find in the table, right, those other readers that can be write down the table in the slot order may finish their critical sections and exit. So we don't necessarily wait sequentially for one reader and then the other and then the third one. So like it's a kind of we wait in parallel for all those readers, even though that we probe just one location in the table.
Thanks.
All right, if there's no more questions, let's thank our speaker again.